This video we will move to consider the boundary condition of the finite element system. Okay. From last clip video, we already formed the global stiffness equation, global equation of the problem, as we obtained the global element stiffness matrix already. But for the case that after we have the equation, we cannot directly solve that equation. Okay, we have to apply the boundary condition first, because actually the element stiffness, the global stiffness matrix, the capital K matrix is a singular matrix. After we so because it is a singular matrix, so it means that the determinant of it is equal to 0. So what does it mean? It means that we cannot finding the solution. We cannot finding the solution from this, because we cannot finding the inverse of this metric, because it is a singular metric, right? So it means that the structural system is unstable if we not apply any boundary condition to that system. So it means that it's the system can have the rigid body motion. It has the rigid body motion. It can move. So it's not stable. It is unstable position. So in general, the number of boundary condition is necessary to make the matrix stiffness to be the non-singular. It should have the boundary, the condition that is constrained enough. Okay, so but the boundary condition is maybe classified into two types. First is the homogeneous boundary condition. That is actually is we familiar with. That is maybe the fixed support, or the support it has no motion. Okay, so this means that the boundary condition that we apply is equal to 0. Okay, and for another one, that is non-homogeneous boundary condition. For non-homogeneous boundary condition is occur when the finite non-zero value of displacement are specified. Okay, for example, the support had a settlement, so it means that the support it has a motion, it's moved according to the settlement. So the displacement at that support is not equal to 0. It has a value or something. So let's consider the first type of the boundary condition. This is the basic one. It is a general one. We will consider the same example that we talking about in last video. That's we have this system of structure that is composed of two spring elements, the element number 1 and element number 2, and we have the boundary condition at node number 1. Node number 1 is fixed. So it means that the displacement at node number 1 is equal to 0. Okay, so according to the global stiffness, according to the global matrix like this. Okay, so when we apply the boundary condition is for this case is u1 equal to 0. When we substitute into this equation, so we will see that at the first row, u1 is equal to 0. So it means that but the F1 that is a reaction force, which is the unknown, we don't know right now. Okay, so according to this, we know already that u1 equal to 0. So it means that u1 is not necessary to find anymore. So we can cutting the first row, we can, because it is not necessary to find. Okay, and if we consider the second and third equation, According when we know that u1 equal to 0, and if we multiply this metric to this vector, and we will see that we will obtain the first equation, second equation, and third equation like this. Okay, for the first equation, we will not consider as at right now. Okay, we will not consider right now because we already know u1. We already know u1, but f1 we don't know, right? But we will finding it after we know u2 and u3. Okay, so we will not consider this equation right now. Okay, so we cancel out, and after that, when we consider the second and third equation, for the second and third equation, we substitute the boundary condition u1 equal to 0 into this equation. So what happened? So it means that the first column, the term of the multiplication with the first column and of the first column to this vector to the first element of this vector, that is u1. So it means that the term of u1 is equal to 0. So it means the term in the first column of the second and third equation is not, it has no meaning because it's multiplied with 0, right? So it means that we can cut off the column and row of this element matrix. Okay, we can cut off this row because we know u1, right? And the first equation is not necessary to solve the unknown u2 and u3 for this moment. Okay, and also we can eliminate the first column also. We can eliminate the first column also because u1 is equal to 0. u1 equal to 0 when we multiply this metric to this. So we have the element of the matrix just only this, that is maybe give us the equation. So after we apply the boundary condition, we will get the equation like this. And from this equation, we found that this equation, this element matrix, is not singular matrix anymore. And we can find the displacement, nodal displacement u2 and u3 from this step. Okay, so this is just the homogeneous boundary condition. Okay, let's move on next. Okay, so if we consider the next condition is maybe non-homogeneous boundary condition. For non-homogeneous boundary condition, what does it mean? It means that the boundary that we have is maybe not equal to 0. Okay, one or more specified displacement are non-zero. Okay, for example, let's consider this case again. But at the support number one, it is not fixed anymore. It has some movement. It has a movement with delta. The movement is defined by delta quantity. And then what does it mean? When we substitute the boundary condition, that is u1 is not equal to 0, but u1 equal to delta. So in the same manner, we can eliminate the first row, Actually, we will not eliminate, but we not consider right now. We just not consider right now. Because we know u1 already. We know u1 already that it is equal to delta. So for the first equation, we will keep it. We will not consider at this moment. We will solve just only for u2 and u3, just for u2 and u3. That is the unknown right now. But the first column it cannot eliminate. The first column it cannot eliminate. Why? Because we have delta. Delta is not equal to 0 anymore. So when we multiply this row to this vector, okay, we obtain this equation. And this equation, okay, we cannot eliminate the term that is multiplied with delta anymore because delta is not equal to 0. So we have to keep it. So let's consider this equation. So what happened? We have this term, right? Minus K1 delta. Okay, according to this, we can rearrange the equation. Into the metric form like this. Okay, and in order to write in terms of U2 and U3 only, so the term of K1 delta should be moved from left to right. This term is moved from left to right. And according to this, we can form the element, the equation to be like this. And the term of force vector is not just only F2 and F3 anymore, but it have the additional term that is K1 delta also. Therefore, what does it mean? It means that when we dealing with the non-homogeneous boundary condition, we cannot initially delete row 1 and column 1 of the equation, okay, corresponding to the non-homogeneous boundary condition. Okay, so because we have the non-zero term that is K1 delta. Okay, so when we dealing with the non-homogeneous equation, so we have to be careful about this also. And then, okay, after we solve the equation already, when we substitute back, we can find the reaction force by this equation. That means that if we know U2 and U3 already, we substitute back into this equation. So we know delta, okay? So we can find the reaction force F1x by using this equation. That is all for the boundary condition. And next we will talking about the next video. We will talking about the example. That's we will procedure we will show you the how to solve the problem, the basic problem that is about the spring system. Okay.